Everybody's got one?
Wait, sir, is it possible to try this class with the lights on? I could see. I don't know if everyone can see, but.
Sure. Let's try. I think we're going to have to go with off. It's kind of hard to see. We'll just try to keep it entertaining to make it worth your while. All right. We'll do the writing while the light's still on, or while it's still light outside. Okay. So first off, well, we covered a lot of ground last time, and actually important stuff. So before I go barreling ahead any further, questions on stuff we talked about last time? Anything that's not kind of making sense, or just really haven't had a chance to digest it yet? Well, let's try a little memory jogger here. So if I have two discrete time sequences, and an input signal x of n has got 300 samples, and I've got a unit sample response h of n for an FIR filter that's 50 samples long, and I want to know if I put x of n into h of n, what's going to come out? What is y of n? Right? Do we do that by convolution? Well, if I wanted to do that using DFTs, that's a lot of samples to do by hand, so we'll look at how we can do that with MATLAB. And just as we suggested that you want to use transforms to do a convolution problem like this because it's generally easier mathematically to do it, to do that for closed form analytical solutions, it's also true it's faster for the computer to do this transforms than it's going to be for to compute a convolution. Turns out a convolution computation is actually pretty easy for a computer to do. It's just multiply, add, multiply, add, multiply, add. In fact, so is a difference equation. Difference equation is multiply, add, multiply, add, multiply, add. So the kinds of computers that have been developed, the kinds of processors that have been developed for digital signal processing, work around that idea. They're really good at multiplying and adding things really fast. So the chips that we call digital signal processing chips, at the heart of them is a hardware unit called a MAC unit. MAC is short for multiply accumulate. It multiplies and adds stuff up really fast, which makes it really efficient for computing difference equations or convolution sums. Also turns out to be pretty good for doing transforms if you're doing discrete Fourier transforms. So let's say we want to do this with DFTs. We want to get a valid linear convolution result for these two. How many samples long do I need my two sequences to be before I transform them if I want to get linear convolution instead of circular convolution? 350? That'll work. Can I make it shorter? $350 works. You could do it with 349. The convolution result for two discrete time signals is going to be the sum of their lengths minus 1. And so technically, if I have 349 samples, that'd be good enough. 350 is fine. So we have to add enough samples. We have to add 49 or 50 samples to x of n, and 299 or 300 samples to h of n, so that they're both now 349 or 350 samples long. And what are those values we're going to add to those extra values we're going to pop in there? What value should we put into those? Zeros. We call that zero padding. Okay. Now, it turns out I might actually want to add more than that if I'm using FFTs, fast Fourier transforms, because they run most efficiently if I have a power of 2 for a length. Well, what length would I choose then for my two arrays? 512, right? So I need at least 349. 256 is 2 to the 8th. 2 to the 9th is 512. I choose the next one higher. Okay. Well, let's look at how you could actually do a convolution, a linear convolution, using discrete Fourier transforms in MATLAB, since most of you have been playing with MATLAB now in 368. Let's write a MATLAB script that convolves two functions. We'll call it DFT CONV, DFT convolve. And we're going to take two arrays, convolve them together, and send the answer out in a variable called y of n. Well, first, we need to figure out how long are the lengths of each of those two input signals, x of n and h of n. How do we do that in MATLAB? Anybody know? Len. No, not len. Length. There's actually a length function in MATLAB that returns the number of values in an array. So call it what you want, some length of x or whatever. I call it n1. But you can use a length function to find out what that is. And do the same for your h of n. And then the length that you want your sequences to be before you transform them, you want them zero padded to a length that's the correct length of the convolution result, which is the sum of these two, maybe minus 1. So we need to compute that length as the sum of n1 plus n2 subtract 1 to 1. And that's the minimum length I need for my convolution result. Now, typically, I'd have to start manipulating arrays and say, well, I got to make an array of zeros now that's n long and drop x of n in the front of that or h of n in front of that, and then do the transforms. But it turns out the clever folks at MathWorks know you're going to need to do this. They know you're going to need to use zero padding, so they make it easy for you. So let's do that convolution using FFTs, the DFTs. And the method, again, is take x of n, make it this long, and take its DFT, which we can use an FFT, fast Fourier transform function for. Take h of n, make it this same length, and take its fast Fourier transform. Then multiply those two transforms, then inverse transform. That would be the steps to do a convolution. Well, so I need to extend x of n to that length and take its Fourier transform. Voila. FFT is the function in MATLAB for taking a fast Fourier transform of some signal, in this case x of n. And because they know you're going to need the zero padded as a second argument, if you give it the length that you want it padded out to, it will do it for you. So we said we need at least an n-length sequence, so I'm going to put the comma n there in the FFT function. And I need to also transform h of n so it looks the same. Some other variable h of k is the fast Fourier transform of h of n with that same length. There shouldn't be a gap between that h and that k. It's all one variable. And then we multiply them. To do the convolution in the time domain is multiplication in the frequency domain, so I'm going to multiply these two guys together to make my y of k. But again, remembering the quirks of MATLAB, if I just put a star there, that tells MATLAB to do matrix multiplication. I want scalar multiplication. I want my x of k has some values, and my h of k has some values, other values. I want my y of k to be this times this to make this, that times that to make that. That's scalar multiplication of two arrays. And then I would get that by using dot star instead of the star. Then we inverse transform. Well, we have a function for that. FFT is a forward transform. IFFT is the inverse transform. So we take the I inverse Fourier transform of y of k. Now, when I do this with MATLAB, a little trick I've learned along the way is x of k and h of k and y of k are all complex valued signals, complex valued arrays. They're real parts and imaginary parts. And they're finite precision. if I convolve two real valued sequences, my convolution result should be real as well. I shouldn't have any imaginary parts left. Turns out, because of the finite precision, when you do this IFFT, you might get something that's got a teeny, teeny, tiny little imaginary part left over. And that's bogus. That's just from rounding error. So you can strip that off with a real function. Usually not a problem, but just a good insurance policy. And so voila, with 1, 2, 3, 4, 5, 6, 7 lines of code, you've got a function that can do a convolution of any length, finite lengths, two finite length sequences of any length, and do it pretty fast. Now, if I had rounded this up to the next power of 2, it would run even faster. And there's even MATLAB functions to help you do that. Any questions on that coding and how to do that? All right, you're all MATLAB experts now. Okay. Well, that's one of the practical ways that we use discrete Fourier transforms. There are other practical limitations that we run into when we're working with real-world signals, and that will raise today's motto. Don't believe every DFT spectrum you meet. They can be very tricky. And here's what goes on in the real world. So I tried to beat home the point on Monday that when we're using DFTs and FFTs, when we use them on finite length sequences, everything can go perfectly well. As long as we choose enough samples that we get all the non-zero ones, transform them, we get the right spectrum, everything's cool, it's great. We can even do that with adding some extra zeros. That would still give me a correct answer, and that might actually be better because the more samples I have in the time domain, I have more samples in the frequency domain, but they're all crowded in the same boundary between 0 and 1, so more samples just means better resolution. And if I have a finite length sequence and I add zeros to it, well, I'm adding real data, so I get just a better resolution, correct spectrum. So for finite length sequences, great. DFT transforms are fine. DFT signal processing is great. But, most of the signals we care about are not finite length sequences. You know, you've got data coming in from a sensor that's coming in constantly. It's really not finite length, it's just constantly coming in. You're just having to process it one chunk of data at a time. But in reality, you're just looking at one time excerpt of a constantly changing signal. Or if you're trying to use convolution for signal analysis, or seeing what applying a filter to a signal using FFT processing and convolution, well, as soon as I talk about having an IIR filter, I have an infinite length impulse response. And but I have to use a finite number of samples with the DFT, so by definition, I'm cutting off some of the impulse response. I'm introducing some error. And so DFT processing can be dangerous. You can get some invalid results if you're not cognizant of this. So if I want strictly correct results, I need the whole signals. I need to see all the data, all the non-zero data, or at least enough of it so that the stuff I'm throwing away is so tiny it doesn't matter anymore. So at best, we usually can get a pretty much right answer. And sometimes, if we're not careful, we can get something that looks pretty wrong, actually. For instance, what about periodic signals? Periodic signals tend to be really long. They're running for long periods of time, and I'm grabbing some samples of them, but those samples represent just some excerpt, some number of cycles, and maybe not even full cycles of a periodic waveform that keeps going on and on and on and on and on. The good news is I'm not as bad off as I thought. Even if I have a really long periodic signal, if I'm clever about how many samples I choose, I'll actually get some really good results. If I don't know what the signal frequency or period is, though, it's hard to get good results with the DFT. Looking at the spectrum of a periodic signal like this, we often get results that we didn't look like at all what we expected. Let's take an example. Here's a analog signal, cosine 2 pi 250t. So it's a 250 hertz analog signal with a amplitude of 1. What's the Fourier transform that it's supposed to look like? What should I see in the spectrum of that perfect cosine?
Delta function.
What's that?
Delta function.
Two delta functions, two spikes. And one at minus 250, one at plus 250. And they should have weights of 1/2. Because the cosine is 1/2 e to the j and then plus 1/2 e to the j other thing. Okay, that's what we would expect. All right, something like that. Okay, let me sample the signal at 2 kilohertz. What should I see in the DFT spectrum of that signal now? How does it change when I sample it? I'm going to dust off those cobwebs for the final.
Shouldn't it stay the same?
It should stay the same. I should still see some spikes there. Is that all that I see now?
Repeats every 2 kilohertz.
What's that?
Repeats every 2 kilohertz.
It repeats every 2 kilohertz. So I get these periodic copies. I take this and I make a copy up here around 2 kilohertz and 4 kilohertz and minus 2 kilohertz. And I get still just 2 spikes. In the principal range, we have what we expected. But now remember, when we're working with the DFT spectrum, we're working with the range from 0 to 1 in digital frequency, or 0 to the sampling rate in analog frequency. So the sample values that I get out of the DFT are covering this range. I should see one spike here at this sample and another spike here near the end. Yeah.
Why is it over that range rather than the principal
It
range?
just is. That's what comes out of the computation. And in fact, there's functions in MATLAB called FFT shift that lets you take that and take that upper end and put it over here to plot so you get the kind of spectrums you're expecting to see. So for graphical purposes, they have that in there. Excuse me. Okay. Well, let's see if we can get, this is the result we expect. If I sample the discrete version of this, if I take the discrete version of this, take some number of samples of it, take it to DFT, I should see something like this, a bunch of zeros, and maybe a 1/2 here and 1/2 there. Well, let's go ahead and do that. Now, the signal that I'm looking at technically is not a finite length signal. It goes on forever. So I'm kind of taking a snapshot in time. I'm taking a finite number of samples of this periodically repeating signal. And I get to choose how many samples I want to take. Let me pull a number out of a hat. Don't have a hat. Let's pull a number out of the air. How about, oh, no, 16. Let's do 16 samples. Why not? It's not too many. It's power 2. It sounds good. All right. So if I take 16 samples at the time domain, how many frequency domain samples am I going to have in my DFT? 32. I take 16 samples, I run them through the DFT computation. How many samples do I get of DFT stuff? And one brave soul in the whole course. Answer is the same number. That was a key thing about the DFT. You put 10 samples in, you get 10 samples out. You put 16 in, you get 16 out. Right? They're always within that range, 0 to 1, without including 1. So that being the case, if I compute the discrete Fourier transform of 16 samples of that cosine, my frequency domain is going to have 16 samples, breaking up a range of 0 to 1, so those samples will be at 0, 1 over 16, 2 over 16, 3 over 16, so on and so on. So my frequency resolution, the space between two adjacent samples, is 1/16 of a cycle per sample. Okay. So again, that's important. important thing about DFTs, same number of samples you put in is the number you get out. Okay, so we take the range of digital frequency from 0 to 1. We're going to get samples at 0, 1 over 16, 2 over 16, 3 over 16, and so on. And if we sample this particular cosine that has a digital frequency of 1/8, and we know the resolution is 1 over 16, we can compute from that actually one of the indexes, index number 2, is going to be where this frequency spike is going to show up. And so we'll see a spike at 2, and we'll also see down from what would have been number 16, we go down to from there and get another one at 14. And in fact, if you did take the DFT of those 16 samples, this is what you would get: 0, 0, 0, 8, 0, 0, 0, 0, 0, 0, 8, 0. So, two things to take away from this picture. Number one, I got spikes exactly where I should have. I got what looks like a valid spectrum. Notice the height is 8, not 1/2. The magnitudes on the discrete Fourier transform are scaled by n, the number of samples. So each of these should have been 1/2, 1/2. Well, 1/2 times 16 is 8. 1/2 times 16 is 8. So there's a little scaling going on there. What else? Well, this is actually a good news story. We took a transform of this, we got a spectrum that we expected, everything looks great. If we were foolish enough to say, I can do better than this, let's get better resolution, let's use not 16, I don't know, let's try 24 samples. That sounds good. We'll get more resolution in here, life should be good. Well, if you take that same signal and sample 24 samples of that signal, take its DFT, here's what you get. Something completely bogus. That is not the spectrum of a cosine. I'm sorry. And the problem is, where that spike wants to fall is not on one of these sample positions. It's halfway in between these two, actually. That frequency should be here in the frequency domain, but I don't have a sample for it. So one way to think about this, and this is not physically true, but it kind of looks like I didn't have a sample there, so the energy that was supposed to be there got kind of moved to the closest samples it could. That's a little bogus, but it's kind of what it looks like, though. But does everybody see the problem? I mean, this should still look like there's two spikes, but it's got this mess. And it's telling me, the worst part about it is, it's telling me I've got signal power in places that it doesn't exist. There ain't no sinusoid at this frequency. None here, none here, none here, none here, none here. Yeah, there's some close to those two guys, but it's lying to me. It's telling me I have signal where I don't. Well, this is what can happen with the DFT. It can lie to you. Well, it turns out it's not really lying. It's a mathematical thing. Mathematical things don't lie, usually. It's just not telling you the answer that you thought it was telling you. If we try to fix this by, I don't know, let's change down to 22 samples, well, and you still get this result. It looks a little better. That's a little closer to the right answer. And if we compare those two, this to this, we'd say, that got a little better. And why that's a little better is, well, the place that that spike should show up is getting closer to there. So we're kind of concentrating things more on this wrong answer. It's not spreading out quite so much. that phenomena of the DFT spectrum telling you have signal where there is not any is a phenomenon we call leakage. It's called spectral leakage. It's like that power, that energy leaked out to places it wasn't supposed to be. And one way to think of it is it comes because we don't have a sample rate at the correct frequency to show that sinusoid exists. But by definition, what we call spectral leakage is when you get what appears to be frequency content and frequencies around the correct one, but at places that don't really exist in the original signal. Well, they didn't. At least we didn't think they did. That's different from aliasing, strictly speaking. Aliasing was, well, we had said stuff was over here at a frequency we couldn't see right, so it went down here. But it turns out that leakage is also an aliasing kind of artifact. So it kind of falls in that same broad category of spectral content where there wouldn't both be any. And it turns out we can actually explain spectral leakage as using aliasing kind of thinking. We'll try to do that. Does everybody see the dilemma? I got a perfect sine wave. I should see a couple of spikes. I got frequency content smooshed out all over the place in my DFT spectrum. So what do you do? Well, it happened because the number of samples I chose was not an exact number of periods of that waveform. If I had taken exactly enough samples to do one full period, or 2 full periods, or 3 or n full periods, that wouldn't have happened. And why that's happening is, again, the DFT is the spectrum not of those samples that I got, but of the periodically extended version of those samples. Right? And so if my periodically extended version of the samples doesn't look like the original signal, its spectrum that I get with the DFT isn't going to look right. Pictures are worth more than words. Here's our original cosine wave, and if I take, well, it's got a period of 8 samples, so let me choose 16 samples, which is exactly 2 periods. And then let me extract that and make the periodically extended version of that time signal, which means I'm going to take that signal, butt up next to it another one, another one, another one, another one. So we do that, put 2 of them back to back, and it's still the same signal, just a longer version of it. Right? If I do that with the 20 samples or the 24 samples, so it's not a exact number of periods, and make the copies of that and put them back to back, that's the signal I have. That's the signal whose spectrum I'm looking at with the DFT. The spectrum not of this thing that I thought I wanted, but the spectrum of this thing that's not what I wanted. So the DFT is right. It's correct. It's the right spectrum for this mess. Because I wasn't careful about how I chose my signal samples so that the periodically extended version resembled the original waveform that I wanted. If I had chosen an exact number of periods, then when I butt them up back to back, they look fine. If I do anything else, I get something different. And this signal does have a spectrum that looks like that leaked spectrum. Yeah?
Is this the same thing we dealt with in lab with the spectrum analyzers?
Yes.
Okay.
And this is why spectrum analyzers have window functions. And we'll see why that isn't, hopefully. So if we take the DFT of this, boom, beautiful. Take the DFT of this, leakage. All right? Because the DFT is the spectrum of the periodically repeating version of the signal we gave it samples for. It's not good. So what do? If you don't have an integer number of periods for a periodic signal, then the periodic extension may have sudden discontinuities. Right? Take a nice waveform and I cut it off here and start another cycle of it here. I've got this sudden vertical jump. What kind of frequencies do I need to make vertical jumps? What kind of frequencies do I need to make square waves? Lots and lots of high-frequency harmonics. So these discontinuities imply I'm creating a signal with really high frequency, and actually these high frequencies are aliasing back into the time creating the leakage, back into the spectrum. So sharp edges in time domain mean high frequencies in the frequency domain. They alias, they give me the leakage. Okay. So how do you get rid of it? Well, if you're smart enough to know, you know what signal's coming in, you know its frequency, well, by all means, choose a number of samples that's an exact number of periods, and everything will be beautiful. Right? Unfortunately, most of the time we're sampling signals. We have no idea what they look like. That's why we're sampling them. We want to measure them. We want to know something about them, so we don't know what their frequency is going to be. And so, by all means, we've got to prevent real live aliasing with anti-aliasing filters. But if you don't know what period you're getting in your waveforms, you're going to need to do something about leakage. What do? Well, first choice, get more samples. How does that help you? Well, if I haven't, like, think of an IIR impulse response. It's dying out, right? So the more samples I take, the more likely those end samples are dying out. I've got pretty much all the data that matters. So that's a good thing. More samples means more samples in the frequency domain, finer spacing. I just increased the probability that I got a sample right at the frequency I need. So you're playing a probability game. Usually that's a little bit impractical. And so what we really do is play with the signals using windowing to make it so we never have these big discontinuities. We multiply our signals by a window function, so we taper them down so they no longer do this. They kind of meet in the middle here. How does that work? So let's say you have a nice sine wave happening at some frequency. I extract a bunch of samples, and notice I didn't choose an exact number of periods here. If I made the periodically extended version of this, I'd have a big discontinuity from here to the next version of that. I'm going to multiply it by a tapering window function, though, before I run it through the DFT. I'm going to taper down the beginning to 0, taper down the end to 0. That gives me not the original blue signal, but the black one. And then let me take the DFT of that guy. So, for example, this sequence, without any windowing, had this very heavily leaked spectrum. If I used a tapered window to taper down the edges so they meet in the middle now, very different looking signal, but its spectrum is actually a little better. Now, the original waveform has a frequency spike here halfway between these two guys. That's what it kind of looks like. That's where it is. Notice I've got pretty much 0 here. I had some big values there. I've reduced the leakage. I can't get rid of it, but I can make it better. And so most signal processors, most signal processing is done with windowing. When I take a finite, I'm using DFTs and I'm using finite blocks of data, processing long data blocks, I'll use a window function. Your spectrum analyzer in 368 had at least 3 different window functions. Had a flat top window, had a uniform window, and had a Hamming or Handing window probably. Those are just different shaped functions that give us different characteristics to do this kind of thing, trying to help the leakage. And there are lots of different kinds of window functions, a myriad different bunch. They all have the general characteristic that they taper down to 0 at the beginning and end. Most of them, an unusual one is a triangular window called a Bartlett window. Most of them are more smooth windows, kind of have a sinusoidal sort of shape, and just vary in how quickly they taper and how smoothly they taper. While their time domain sample values look pretty similar, their frequency domain, their Fourier transforms, are same basic shape, but have different characteristics that make us choose one over another depending on our what application we're going to put them towards. Notice they all have kind of a main center lobe here, and then a bunch of lobe bounces below. Well, think of the simplest window, a rectangle window. If I take an infinitely long bunch of data and I extract 8 samples, to the mathematicians, that's like multiplying that infinitely long sequence by a rectangular window function that has 1s over those 8 samples and 0s everywhere else. Okay. So I'm just multiplying by 1s, a rectangle function in the time domain. What's going on in the frequency domain? What's the Fourier transform of that rectangle function? Sinc function. Sinc function has a center lobe and a bunch of bouncy side lobes. So all of these are sinc-like kind of functions in the frequency domain. Thank you. No, it's only up there. That's interesting. And what matters to me in their spectrum is how wide is that main lobe and how far down are these side lobes. And so those are 2 key characteristics of window functions that we always look at, the main lobe width and the side lobe height or side lobe attenuation. The effect of using window, we're multiplying our signal by some window function in the time domain, or limited, and we're not doing that. We know that if we convolve 2 functions in the time domain, we multiply their spectra. We're multiplying stuff in the time domain, which means we're convolving their spectra, right? That's duality, Fourier transforms. So, if I take this signal with a beautiful transform and multiply it by a window function, even a rectangular window function, to truncate it, that has a sinc-like Fourier transform, the result of this multiplication, a truncated sine wave, is this spectrum convolved with that spectrum, which, think of these as impulses. I'm going to pick this up and make a copy here, pick it up and make a copy there, and have all these little bumps and doodads. So the effect of windowing is to take my beautiful original spectrum and spread it out in the middle and make extra bumps where there aren't stuff. Which doesn't seem like a good thing to do. Everybody see what's happening? It's because we're multiplying stuff in the time domain, we convolve their spectra, and that has the effect of spreading things out and giving me possibilities of having stuff showing up where it's not supposed to be. And what I'm going to care about is how wide is this main lobe of the window function, because when I do that convolution, what it's going to do, if that's too wide, if I have 2 frequency spikes right close to each other, I convolve them with this mess, I get a wide mess that I can't tell what it is. So if I have 2 spikes and I convolve a wide sinc function with them, the sum of those is a big mess with just maybe a little tiny dip in it. And I look at that spectrum, I can't tell you, is there 1 or 2 spikes in there anymore. I've lost the ability to resolve multiple spikes at nearby frequencies. That's frequency resolution. So windowing hurts the frequency resolution of my spectrum. If I have big side lobes, I get this extra stuff going on here. If I really truly have a big signal here, and I really truly have a little signal right here, it could be lost. I can't tell with this kind of leak spectrum, is that leakage or is that a real signal? So the side lobes mess up my dynamic range resolution, my ability to resolve low signals in the presence of big signals when I have leakage or when I do windowing. Okay? So what you'd like to fix both of those, you want really narrow main lobe windows and really low side lobe windows. Unfortunately, Mother Nature says pick one or the other, you can't have both. They are mutually exclusive. If we ran back, I should put the slide here in this slide, the windows that have really low side lobes, notice, like this guy, like the Blackman window, has a really wide main lobe. And the ones with the narrower main lobes have really high side lobes. And the king of narrow main lobes is the rectangular window. But it's got full-fledged sink, big bumps on the side lobes. It's the worst side lobe. So that's why you got 3 settings on your spectrum analyzer. Do you need frequency resolution, or do you need dynamic range resolution, or some mix in between? You're trading off what window function based on what kind of measurement you're trying to make. So yeah. And we can use this whole windowing understanding to also explain leakage. Okay. So when we take a periodic signal and we extract a finite number of samples, that's the same as multiplying it, as we said, by a rectangular window that's as long as the number of samples we want to take. So we are convolving our nice spike with a sync function, and so the blue is the true DFT spectrum of that windowed combination, and the DFT is giving us samples of it that in this particular case happen to fall here and there on the main lobe and at the peaks of all these side lobes, giving us all that leakage. And it's completely unavoidable. Even if we did everything right and sampled for an exact number of periods, like with this example, the windowing effects are still there. We didn't undo them. It's just that everything worked out just right so that this sample where the spike belongs is centered around the peak of our main lobe. And the 0 crossings on all the side lobes fell right exactly where the samples were in our DFT spectrum. So it's not like something's happening and not happening. It's always there. Just that we're catching it in just the right set of conditions when we choose the right number of samples. Yeah.
I'm kind of confused. Didn't we apply the windowing to counteract the leakage?
So extracting a finite number of samples is windowing it by a rectangular window. So that comes, so its effects come no matter what. I can take that data and window it again with a tapered function and improve on this to help the leakage. I can change the characteristics of that function that I'm convolving with to make the leakage less noticeable. But you're right, you're double windowing basically. Yeah.
So yeah, you're like convolving with like one with a narrow middle lobe, and then convolving with one with small side lobes.
Instead of getting the best of both worlds, you get the worst of both worlds. Yeah. You're always giving up something in each of those processes. Would be nice though, could. Okay. So even when we do things right, this truncation effect is still showing up. It's just very benign. And if we are smart enough to be able to do this, this is all we would do. But usually, again, we don't know what frequencies are coming in. We are going to get some leakage. So in that case, we'll apply another window to try to improve the leakage to do a better job of looking at the spectrum. So again, leakage is a spreading out of the signal energy across the frequency domain. It's due to the effects of truncating, grabbing out a finite number of samples from an infinite length sequence or a periodic sequence. If you know what the signal period is and you can choose the number of samples to be an exact number of periods, great, go for it. It'll give you the correct spectrum. If you can't, the best you can do is probably apply a windowing function where you're going to choose a trade-off between the width of the main lobe and the side lobe height, depending what kind of resolution you need, what kind of measurement you're making. And Every time we do a windowing, though, it has the consequence of hurting one resolution or the other, so we have to be able to accept that with our application. So that's the real world stuff that goes on with DFT processing. It seems like a lot of headache. Why do we even bother? Well, again, watch your eyes, light's coming up. We do it because the DFT can be computed with a computer, can be computed very efficiently with a computer, very fast. And so, because it's just a sum, and it can be actually computed in digital hardware pretty easily because it's just a bunch of multiplies and adds. And so it's really amenable for doing this kind of stuff in the context of computer or digital hardware, where everything is perfect. Right? No mathematical errors possible. And everything can be done fast and digitally and transported. It never changes. So it's a really powerful technique, so much so that we learn to live with these shortcomings. How many of you noticed leakage when you were looking at FFT spectrums in your 368 lab? You saw, what's that stuff doing there? Yeah, this is where it was coming from. It's a consequence of DFTs. Window is what we do try to solve it. Friday we'll talk a little about some applications, we'll talk about the midterms again, try to get you set up for the final. Again, if I didn't mention it, did I mention there's an online survey? Oh, before you go, in my last minute, you've probably been dinged by the university to do a course evaluation for all your courses. Please do that for my course. I appreciate the feedback. On PolyLearn is also a more detailed course evaluation, gives me better feedback of what stuff's going good, bad, not. So much so that I'm going to make it worth your while. If you fill out this survey, which is anonymous, but I get the aggregated results at the end. If you fill it out, you will get inserted an additional quiz in the grade book that will show up with a grade of 100. So no matter what you say about me, you get 100% on the quiz. So take a look at that. It's in the PolyLearn bottom block about the final exam. Check it out. See you Friday.